So this is the last part, part C, under the same question we've been studying up to now. So same question now. I have made a small change here. Now imagine instead of a uniform string, now this particle is attached to two different string of natural length L. Not the midpoint, attached to two strings two elastic strings of same length. Now natural length is L. Elastic modulus are given here. String in this part AO has an elastic modulus of 2 mg. String in this part OB has an elastic modulus of mg. Now the elastic modulus are different. Right. So what is part C about? Provided elastic modulus in AO part is 2 mg and OB part is mg. I have mentioned them in the diagram. Now if U is given, U velocity is given at O when the particle is at here, velocity is given. Now since their natural lengths are L and L, the particle will stay at rest initially. The equilibrium point would be O. Find the amplitude in each side. Now what happens due to this difference in elastic modulus, the amplitude in each case will be different. So amplitude on this side is not the same as the amplitude on this side. So this is actually two different types of simple harmonic motions of different omegas. We'll see the omega will be different in each case. So this is actually a combination of two different simple harmonic motion, but still the particle will be under simple harmonic motion. So at the end, we're going to combine these two. So O, find the amplitude. This is the first thing you do in each case, and the period. Then you have to find the period. Right. So for this part, we have already shown it because the lambda was initially mg. So this is the characteristic equation. And based on this, we have found the amplitude on this side. A1 would be U times root L over G. Now we'll look into this side. So now this is the position on this side, x distance. So in this direction, x double dot is increasing. So we'll put F equal ma to the right hand side. Then t is positive. Now t2. This becomes minus mx double dot. Here the tension would be lambda is 2 mg times x over L minus mx double dot. M cancels out, and finally you get 2g over L root squared minus x equal x double dot. This is the characteristic equation of the motion of the particle when the particle is on this side AO. So notice here there are two different omega values. For this, omega is now omega 1. Let's say omega AO would be root 2g over L, and omega OB would be root g over L. So now you know that this is a combination of two different simple harmonic motions. On this side you have one type, on this side you have another. So you have what is the amplitude in each case. To find the amplitude in AO direction, we use the same equation. So when it goes to the when it moves in this direction, suppose it is move the u is given in this direction, so it moves until it reaches its amplitude, then turns around, comes back. At O, you have the velocity u again because it is symmetric. So at this point, the velocity is u again. Then it moves on to the other side. So the starting velocity is u. So u squared is equal to omega AO squared A2. Let's call it A2 squared minus x squared. Again, x is 0. You can see in either of cases the center is still O, the equilibrium point, and therefore u squared A would be less A2. Let's write A2, then u times u divided by omega AO. This would be L over 2g, root L over 2g. So notice the difference here. So A2 now, what is A2? U times root L over G means A1. This is A1. So other than that, there's root 2. So you can see that the displacement on this side is greater than the displacement on the other side. Why is it different? Why is it different? Because the lambda 1 is 2 mg on this side. Lambda 1 elastic modulus is higher on this direction. If the elastic modulus is higher, then consequently the amplitude will be lower. That means you need a lot of energy to make the same displacement, right? When the elastic modulus is high. So that's why A2 is different. So in the final picture, let's say the amplitude on this side is like A2 here, then the amplitude on this side would be much longer, A1. So like this. Right, then find the period. Period means the time it takes to move a complete cycle. So for this part, you know, it start from here, moves until A1, then comes back. So this is actually 1/2 of the cycle. So the total time would be T0 to A1, then A1 to O. So that is pi divided by, now not 2 pi, this is just half of the cycle, so pi divided by omega 1. Omega 1 means root g over L. Root g over L, therefore this is L over g, root. Then plus pi divided by this part here, so L over 2g. So the total time now being, you can factor out an pi here, pi and L over g, root. Then you have 1 plus 1 over root 2. 1 plus 1 over 2. This is the total time period. Right. Thank you for watching.